Alright, this video is going to be the first video of, I think, 3 videos on section 6.3, and we're going to be looking at Taylor and Maclaurin series. So we have the definition of Taylor and Maclaurin series here. If f has derivatives of all orders at x equals a, then the Taylor series for the function f at a is the sum n equals 0 to infinity, the nth derivative evaluated at a divided by n factorial, and then times x minus a to the nth power, which is equal to f of a plus f prime of a x minus a plus f double prime of a over 2 factorial x minus a plus dot 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 the nth derivative evaluated at a divided by n factorial times x minus a to the n, etc. So that's what the Taylor series is. A Maclaurin series would be a Taylor series specifically centered at 0. Okay. Alright, so let's go and get a couple more items here. So we got this big old long list here, and it says to consider the function f of x with a power series representation centered at x equals a. So f of x is equal to the sum n equals 0 to infinity c sub n x minus a to the n power, which is equal to c naught plus c1 x minus a plus c2 x minus a squared plus dot 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 plus c sub n x minus a to the n, and it keeps going. Now if we evaluate the series at a, f of a is going to be c naught because everything else is going to absorb. Well, what about the derivative? If we take the derivative of f of x, the c naught would be 0, then we'd have c1 plus 2c2 x minus a plus dot 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 all the way out to n c sub n x minus a to the n minus 1, and it would keep going. Now if we evaluate the first derivative at a, that would be equal to c1. Everything else has an x minus a, and so that's all going to absorb. Okay. Alright. Now if we look at the second derivative of f, that's going to be 2c2, and then the next term would be 3 times 2c3 x minus a plus dot 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 n minus 1 c sub n x minus a to the n minus 2, and that would keep going. If we evaluated the second derivative at a, everything would absorb except for the 2c2. Okay, if we solve for the coefficient c2, c2 would be equal to f double prime evaluated at a divided by 2. Let's look at the third derivative. If we look at the third derivative, it's going to be 3 times 2c3 plus 4 times 3 times 2c4 x minus a plus dot 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 n minus 1 n minus 2 c sub n x minus a to the n minus 3. If we evaluate this at a, everything is going to absorb except for the 3 times 2c3. So f triple prime of a is equal to 6c3. So if we solve for c3, c3 would be equal to f triple prime of a over 6, or we could rewrite that as f triple prime of a over 3 factorial. The fourth derivative would be 4 times 3 times 2c4 plus 5 times 4 times 3 times 2. I think we got an extra thing in there. I've got a little mistake here, so this 2 right here shouldn't be here because we're taking the derivative. No, wait, it's okay. Because here we're taking the derivative the fourth time, so this would be 4 times 3 times 2 times 1, so 4 times. Okay, so that's all right. Sorry about that. Okay. So anyways, the fourth derivative there, if we evaluate the fourth derivative at a, everything else will absorb except for the 4 times 3 times 2, which is 24, and so we would have the fourth derivative evaluated at a equals 24c4. So if we solve for c4, we'd have c4 is equal to the fourth derivative evaluated at a all over 24. So ignore this is a typo. Okay, and that is equal to the fourth derivative evaluated at a, and 4 factorial is the same thing as 24. Okay, now if we continue this process, the nth derivative would be n minus 1, n minus 2, n minus 3, all the way out to 2 times 1, c sub n. And then if we wrote down the next term, it would be n plus 1, n minus 1, dot, 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 3 times 2, c sub n plus 1, x minus a. If we evaluate that at a, everything after the nth term is going to go away. So the nth derivative evaluated at a is going to be equal to n minus 1, n minus 2, dot, 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 2 times 1, c sub n, which it can be rewritten as n factorial c sub n. So we can solve for c sub n, and c sub n would be the nth derivative evaluated at a all over n factorial. And so what we're noticing here is we're able to come up with an explicit formula for the c sub n's. And so we have a result from the previous section that said something about the uniqueness of a Taylor series, or a uniqueness of power series, and then we'll combine that with the Taylor series. So theorem uniqueness of a Taylor series: if a function f has a power series at a that converges to f on some open interval I containing a, then that power series is a Taylor series for f at a. And so that last slide we showed kind of how that goes about, how we find that c sub n. Alright, now let's talk about the definition of a Taylor polynomial. If f has n derivatives at x equals a, then the nth Taylor polynomial for f at x equals a is p sub n of x, which is equal to f of a, plus f prime of a, x minus a, plus f double prime of a over 2 factorial, x minus a squared, plus f triple prime of a all over 3 factorial, x minus a cubed, plus dot, dot, dot. The nth derivative evaluated at a all over n factorial, x minus a to the nth power. And so we'll do an example or two of how to find these Taylor polynomials. Okay, so we're going to construct a 5th degree Taylor polynomial centered at x equals 2 for the function f of x equals e to the negative x. And so what we're going to do is we're going to take repeated derivatives. We're going to take the derivative of e to the negative x until we get to the 5th derivative, and I'm going to evaluate each one of those derivatives at negative 2. So f of x is e to the negative x. First derivative would be negative e to the negative x. Second derivative would be e to the negative x. Third derivative would be negative e to the negative x. Fourth derivative would be e to the negative x, and the 5th derivative would be negative e to the negative x. So now we're going to evaluate, since it's centered at 2, we're going to evaluate each one at 2. So this is going to be f of 2 is e to the negative 2, f prime of 2 is equal to e to the negative 2, f triple prime of 2 is e to the negative 2. The third derivative evaluated at 2 would be negative e to the negative 2. Fourth derivative evaluated at 2 would be e to the negative 2, and the 5th derivative evaluated at 2 is equal to negative e to the negative 2. Now what I'm going to do is I'm going to write out all the Taylor polynomials up to the 5th degree. Okay, so the first Taylor polynomial is going to be just f of 2, which is e to the negative 2. The second Taylor polynomial, or first degree Taylor polynomial, is going to be e to the negative 2 minus f prime of 2, which is negative e to the negative 2, and then x minus 2 to the first power. The second ordered Taylor polynomial will be the first degree Taylor polynomial, and then we just add one more term to it. And the next term, f double prime of 2 is e to the negative 2, x minus 2 squared, and then over 2 factorial. The third degree Taylor polynomial will first have the second degree Taylor polynomial, and we'll just have one more piece to it. And that new piece will be f triple prime evaluated at 2, which is negative e to the negative 2, x minus 2 to the third power divided by 3 factorial. The fourth degree Taylor polynomial centered at 2 is going to be the third degree Taylor polynomial, and we'll just have one more extra term to it. And that new term will be f, the fourth derivative of f evaluated at 2, which would be e to the negative 2, x minus 2 to the fourth over 4 factorial. And the fifth degree Taylor polynomial will be the fourth degree Taylor polynomial plus the last term. So we'll write it out until we get there. So there's our fourth degree Taylor polynomial, and so now we just need to add on to it the next term. So the fifth derivative evaluated at 2 is negative e to the negative 2, x minus 2 to the fifth power all over 5 factorial. And so here's your fifth degree Taylor polynomial centered at 2 for e to the minus x. And so what we're going to do is we're going to, on the next series of slides, is we're going to graph e to the minus x, and then we're going to graph each one of the Taylor polynomials starting with the 0 degree through the 5th degree. Okay? So here's the first one, and we have e to the minus x matched with the 0 degree Taylor polynomial, y equals e to the negative x. And so they are going to agree at the point here 2 comma e to the negative 2. So they agree right there, and that's pretty much it. Okay, and you can see that maybe they look sort of close to each other around 2. Okay, now the second Taylor polynomial, or the first order Taylor polynomial, first degree Taylor polynomial, is going to look like this one here. So it's going to be a line, and you see that it does do a better job of approximating the function around 2. Okay, and so now we've matched it so it'll go through the point 2, negative 2, and it also has the same slope at 2. And then when we get into the quadratic, it gets a little bit better. So if we get to the quadratic, it's a little bit better. So not only is the value of the function agrees, but the first derivative agrees, and so does the second derivative. So we have the same point, the same slope, and the same concavity at that location. Okay, getting into the third degree gets even better. Okay, and you can see that the cubic here does a pretty good job of approximating e to the negative x around 2. And then here's the fourth power. It looks even better. And the fifth power is getting even better. So as long as you stay close to 2, this Taylor polynomial can actually tell you values of e to the minus x, but instead of calculating what e to the, negative 2.1 is, we would plug it into a Taylor polynomial, and we get a little bit better. We'd use a polynomial, and well, it's not quite a polynomial because, well, depending on how we do polynomials, if we say we have real coefficients or not. I said we'll say we have real coefficients. So yeah, we're using a polynomial. Sometimes we have integer coefficients, rational coefficients. But anyways, I'm getting off track here. So we could use our polynomial as opposed to using the calculator. Well, I guess we'd be kind of stuck either way with this one because it's e to the minus 2. So maybe this is not the best example in the sense of using this to make approximations. But the point being here is you can tell that it is doing a pretty good job of approximating the function around 2. So later on we'll get a better example where we can approximate a function with a polynomial that maybe we wouldn't really have to use a fancy calculator. Here's the last slide here, and well, what happened? Maybe I didn't put it on there. Okay, so let's go ahead and look at another example here. So we're going to do example number 2, and we're going to construct a 4th degree Taylor polynomial centered at 0. So this would be a Maclaurin polynomial for the function f of x equals x over x plus 1. Okay, so we're going to start off with f of x is equal to x over x plus 1. First derivative is going to be x plus 1 times 1 minus x times 1 over x plus 1 squared, and so the first derivative will simplify down to 1 over x plus 1 squared. Second derivative will be negative 2 over x plus 1 cubed. Third derivative will be equal to 6 over x plus 1 to the 4th power, and the fourth derivative will be minus 24 over x plus 1 to the 5th power. Okay, and so we're centered at 0, so this is a Maclaurin polynomial, but we're going to go ahead and evaluate. So it is Taylor, it is Maclaurin, so we're going to evaluate each one of these at 0. So f of 0 is 0. F prime of 0 is 1, f double prime of 0 is negative 2, f triple prime of 0 is equal to 6, and the fourth derivative evaluated at 0 is minus 24. So then our 0 Taylor polynomial is going to be 0, and then the first degree Taylor polynomial is going to be x. Second degree Taylor polynomial is going to be x minus 2 x squared over 2 factorial, which is going to be x minus x squared. The third degree Taylor polynomial is going to be x minus 2x squared over 2 factorial plus 6x cubed over 3 factorial, which is going to be x minus x squared plus x cubed. 3 factorial is 3 times 2 times 1, which is going to be 6. Okay, and the fourth degree Taylor polynomial is going to be x minus 2x squared over 2 factorial plus 6x cubed over 3 factorial minus 24x to the fourth over 4 factorial. And that's going to be x minus x squared plus x cubed, and 24 is 4 factorial. 4 times 3 times 2 times 1 is going to be 24, and so that last term is going to be negative x to the fourth. Okay. And again, if you wanted to, you could graph these and you'd see that around 0, these Taylor polynomials would be getting closer and closer to x over x plus 1 in terms of approximation. Alright, so thanks for hanging on, and let's do one more example here. And let's construct a second degree Taylor polynomial centered at pi over 2. And this will be for the function natural log of 1 plus x. Okay, so f of x is equal to the natural log of 1 plus x, or x plus 1. First derivative of x is equal to 1 over x plus 1, and the second derivative is going to be negative 1 over x plus 1 squared. So now we're going to evaluate each one of these at pi over 2. So natural log of pi over 2 plus 1. F prime of x, f prime of pi over 2 is going to be 1 over pi over 2 plus 1. F double prime at pi over 2 is going to be negative 1 over pi over 2 plus 1 squared. Simplify these down. So f evaluated pi over 2 is going to be the natural log of pi plus 2 over 2. F prime evaluated pi over 2 is going to be 2 over pi plus 2. And F double prime at pi over 2 is going to be negative 4 over pi plus 2 quantity squared. The zeroth Taylor polynomial is going to be natural log of pi plus 2 over 2. The first degree Taylor polynomial is going to be the natural log of pi plus 2 over 2 plus 2 over pi plus 2 x minus pi over 2. The second order Taylor polynomial is going to be the natural log of pi plus 2 over 2 plus 2 over pi plus 2 x minus pi over 2 squared. Sorry, not squared, not yet. Minus 4 over pi plus 2 squared, and then x minus pi over 2 squared. That's where we want the square. Okay, and all over 2 factorial. So we went by that real quick. So over 2 factorial. Oops. There we go. Over 2 factorial. So 2 factorial is 2 times 1, which is 2. Divide that into the 4, and that'll knock it down to a 2. Okay, and that is our second degree Taylor polynomial centered at pi over 2 for the natural log of x plus 1. And so I hope you feel better about constructing Taylor and Maclaurin polynomials. And stay tuned for the next video.